Now we will discuss situations in which a limit may not exist. If you've seen the movie Mean Girls, you know that this can happen already. There are three common reasons that cause a limit to not exist. One is if the function approaches a different number from the right side of C than it approaches from the left side of C. A second is if the function increases or decreases without bound as x approaches C. A third is if the function oscillates or moves up and down quickly between two values as x approaches c. We actually won't see this one in our course, as this happens with trigonometric functions, and we don't study those in APM 105. We will, however, see the first two reasons. Let's get more detailed about the first reason. If we have a function that approaches a different number from the right and the left side of c, then we have to be able to talk about this behavior. We call this idea one-sided limits. So far, all of the limits that we have been talking about have been what are called two-sided limits. I haven't really called them two-sided limits because we haven't had a reason to distinguish them from one-sided limits. However, now we will. So sometimes when we are only interested in what the function approaches, as x approaches c from one side, only the left or the right, we will use what are called one-sided limits. We need to develop notation that will distinguish one-sided limits from two-sided limits. If we use the same notation, the lim or limit as x approaches c of f of x, and say that that is equal to L, but we only want to talk about x approaching c from, say, the right-hand side, then we put this little superscript, or kind of like in the place of an exponent, we put a plus there. This means that we're coming from more positive on the number line, or we are approaching from the right. Graphically, what this will look like is you are heading towards the value of x equals c, but you're coming from the right-hand side. So we can see that the graph of this function is going towards the y value of L as we only look as x approaches c from that one side from the right. Now it's a little confusing because you are moving to the left, but with limits, we have to decide which thing we're going to use. Is it the direction we're moving or the direction we're coming from? And sometime long ago, someone decided we're just going to use the direction we're coming from. So from the right-hand side moves to the left, but I just like to think of this plus here, meaning with numbers more positive on the number line and heading towards C, so from the right. On the other hand, if we want to talk about x approaching c but from the other direction, from the left-hand side, we use the same notation, but instead of a plus in the little superscript, we use a minus. So this means the limit of f of x as x approaches c from the left-hand side now is this letter I'm calling k. So again, here we will use numbers that are smaller than c to plug into the function, or look as x approaches c, but from the left-hand side, if you're looking at a graph. So we can see here that we're only going to look at this part of the graph, and we're looking at what the y values are approaching as we get closer to c, and so that will give us a value of k. Now, if you're wondering why it is k here, even though it's filled in up here at L, remember that with limits, we don't care what happens at the value x equals c. We're just taking our best guess of what we would kind of expect to happen as we get to see if we didn't know what happened there. Right? The approaching means we are never actually getting to c, we're just getting closer and closer and closer. So if we do that on the left-hand side here, we would expect that the y value would be k there if we didn't know any better. Now, sometimes, in the case of this graphical example here, we see that from the right-hand side and from the left-hand side, there's kind of a discrepancy in what the function is doing. Right? We are approaching L from the right and k from the left. There is what we would call a jump in the graph here, or a disconnect, or we'll talk about this later, but a discontinuity. When this happens, if the left-handed limit here does not equal the right-handed limit here, if they are not the same, then what we say about the two-sided limit is that it does not exist, or DNE for short. So again, in the case here, if we were looking at the two-sided limit, we would say that this is DNE, or does not exist. On the other hand, if these do meet up and there's maybe just a hole there, or maybe it's filled in, then we would say that the limit from both sides, the two-sided limit, does exist, and it's equal to whatever value that we find by investigating the function. So let's look at some examples of functions where this can happen. In example 1, we have a piecewise function. F of x equals 5 minus 2x if x is greater than 2, and f of x equals x minus 3 if x is less than or equal to 2. The first thing we should do is graph this function. Now in your calculator, there is not really a good way to graph a piecewise function. It will overlap the two formulas if you put them in separately. I do expect that you can graph something like this by hand fairly easily. So the best thing that we can do is make a table of values. I would suggest making two tables of values here, one for each of these kind of formulas. So for the first one, let's make a chart with x and f of x. It doesn't matter what order that we decide to do this in, but maybe first we could do the values of x that are less than or equal to 2. So let's pick some values here. I'm going to plug in a 2 and something that's less than or equal to 2, so we already have the equal to, so maybe we'll do 1 and 0. We only need a couple points. We're going to substitute these in to the formula x minus 3 because these x values are less than 2. So when we do 0 minus 3, that's negative 3. We have 1 minus 3, that's negative 2. And then 2 minus 3 is negative 1. Now here, because we are following the formula when x is equal to 2, on our graph, this is going to be a filled-in circle at 2. Then we have to figure out what's happening with the other piece of this function here. We can do the same thing and make a table, x and f of x. Here, we're going to be plugging in values that are larger than 2. We should still see what's happening around 2, so we can kind of plug in a 2 here with the understanding that we're going to have an open circle on the graph at this point. Then we'll plug in some values that are bigger than 2, so how about 3 and 4? To find the y values, we're going to be following this formula here, 5 minus 2x. If I plug in a 2 into 5 minus 2x, we get 5 minus 4. That gives us 1. When we plug a 3 into 5 minus 2x, that gives us 5 minus 6, and so that's negative 1. And when we plug a 4 into 5 minus 2x, we get 5 minus 8, which gives us negative 3. Now we should know the general sense of the shape of these graphs here. These are both linear equations because we've got x to the first, x to the first. This one will have a negative slope, this one will have a positive slope, and the intercepts will be different. You could, with that knowledge, plot this graph as well, or you can make a table of values here and connect the points together in a line because you understand that these are linear equations. So let's start by plotting some points. At 0, we've got a y value of negative 3, so that's down here. At 1, we have a y value of negative 2, so there's that other point. And at 2, we have a y value of negative 1, and I'm going to make this point here filled in and solid because we are following this equation here, which is true when x is equal to 2. Now this is good for less than 2, so that's all of the points that are over here. So I'm going to connect these together. I know that it's a line, so there's the general shape of it. Now the other part of this graph, for x greater than 2, it's going to be different on this side of 2. So we can still plot the points. We found that when x is 2, y is 1. When x is 2 and y is 1, we're going to have an open circle because we are not going to be using this formula here when we have x equal to 2. So we've got a filled in dot down here. When x is 3, y is negative 1, so that's the point down here. We will fill that in. And when x is 4, we have y is negative 3. So that's this point down here. I know this is a line and it's got a negative slope, so I can connect these together and just kind of extend the graph to look like this. Now in part B, we are asked to find the limit as x approaches 2, and then this minus sign means from the left-hand side. So this where we are approaching 2, but with numbers that are smaller than 2. Or graphically, we're approaching 2 from the left, so from this direction. Now we can see from the graph that the y value here is negative 1. Again, we cover up what's happening. We're only following the graph that is approaching 2 from the left side, which is just blue 1. We don't care what's filled in or what's not filled in. Just where does it look like it's heading towards? Again, that y value is of course negative 1. So the limit for part B is going to be negative 1. In part C, we find the limit as x approaches 2 from the right-hand side, which is what this plus indicates. We are following the graph of the pink line here, because this is x values that are larger than 2. Now again, if we didn't know any better at all about what's happening at 2, or even to the left of 2, we don't care. What does it look like the y value are heading towards? And of course, that here is equal to positive 1. Again, this is just open circle here. We don't care what happens at 2, just as we're approaching 2, but with numbers larger than 2. So the right-sided limit here will be positive 1. In part D, we are finding the two-sided limit. The limit as x approaches 2 without a plus or a minus here. And that is a two-sided limit. Now remember that when the limit from the left side and the limit from the right side don't match up, or when there's this kind of jump in the graph, then the two-sided limit here, we would say does not exist. To write that out in symbols to explain our reasoning, we would say that the limit as x approaches 2 from the left-hand side is not equal to the limit as x approaches 2 from the right-hand side, because we've got -1 and 1, and those are not the same. So that is enough for us to say that the two-sided limit as x approaches 2 of the function dne, or does not exist. So these types of functions, which are again called piecewise functions, they tend to sometimes have jumps in the graph that look like this at the point where they split their formula. This won't always be the case. If we had this point here kind of matching up, like if this line were maybe moved up 2 spaces, then they would meet at the same point. It would be a kind of rough transition to have this kind of corner place here, but the limits would be the same from the left and the right-hand side. In that case, we would say that the limit does exist, and it would be equal to whatever we have for the individual one-sided limits. But if they are different, then this is when we say the limit does not exist. Another type of function in which we can sometimes see a limit not existing is a function that involves absolute value. So in example 2, let's find the limit as x approaches 1 of the absolute value of x minus 1 divided by x minus 1. Now, I told you some time ago that the first thing that we should try is plugging in a 1 into the function. If we plug in a 1 here, we get the absolute value of 1 minus 1 over 1 minus 1, and that gives us 0 over 0. That can indicate a hole in the graph or a jump or some kind of break, possibly. But in any case, no matter what's happening, this is undefined. It tells us to do more work and figure out what's going on in the graph at that point. Now we can see that if we look at the graph of this function, at 1, there is this jump. We can't plug in a 1, so both of these kind of points here will have open circles. Although if you do graph this in your graphing calculator, it will kind of look like they're both filled in. Again, our calculators are only approximations of what graphs look like most of the time. We have to understand how a function is and kind of add some pieces that our graphing calculator can't necessarily give us. So based on what we've been talking about with one-sided limits, we should be able to see here that the two-sided limit as x approaches 1 isn't going to exist. Let's see how we could also determine that numerically. So please take a second and pause this video and see if you can set up a number chart with a center at 1, because our initial question is as x approaches 1 from both sides, and plug some values in and see what you get out. So the numbers that you should choose from the left and the right of 1 should probably look something like this: 0.9, 0.99, and 0.999 to approach 1 from the left, and then 1.1, 1.01, and 1.001 to approach 1 from the right. Then when you plug each of these values into the function absolute value of x minus 1 divided by x minus 1, you'll get the following numbers. So when you plug a 1.1 in, you should get a 1. When you plug a 1.01 in, you should also get a 1. And when you plug a 1.001 in, you also get a 1. If you're not sure where the absolute value button is in your calculator, it should be under the math button if you have a TI calculator, and then go over to num, 1 to the right, and you should see ABS, which is the first option. If you hit enter, then it should pop up in your home screen and you can substitute in whatever you're trying to plug in. If you plug in 0.9, 0.99, and 0.999, you should find that each of those values actually gives you -1. If you're not getting these, try one more time, and again, we can meet and discuss how to do this in your particular calculator. So the way that we would describe this behavior is, well, from the left-hand side, we're not really getting closer to a particular number. They're actually just staying the same. And when that's the case, that's just the limit. So from the left-hand side, we would say the limit as x approaches 1 from the left of the absolute value of x minus 1 divided by x minus 1, that's -1. On the other side, as you approach 1 from the right, we again have this constant behavior where we just have 1, 1, 1 all the time. If we get closer to this one, then we'll have another just 1 here. So when that's the case, we've got this behavior, the limit as x approaches 1 from the right-hand side of x minus 1 divided by x minus 1. That is now +1. We can see this in the graph because if we approach x equals 1 here from the left-hand side, our y values are down here at -1. And we can also see that as we approach x equals 1 from the right-hand side, the y values are all approaching +1. And because we have this kind of discrepancy between what's happening from the left and the right, they're not in agreement, right? When that happens, when the left and the right limits are not equal to each other, then what we say is that the limit from both sides, which is the limit that we were looking to find in the first place, the one that doesn't have a plus or a minus in the superscript right here, the limit from two sides is, well, doesn't equal anything. Does not exist. So it's just d and e. There is no value that the function approaches from both sides. So we should be able to tell a one-sided limit using a table like this, using a graph, either side, left or right. We should also be able to determine if a two-sided limit doesn't exist by looking at a table or a chart, and also know what that looks like by looking at a graph. So we just saw some examples of limits that don't exist because the function approaches a different number from the left and from the right. The second reason that we have a limit not existing could be unbounded behavior as you approach a certain number. Let's take a look and see what that looks like. In this example, we have the function f of x equals 1 over x plus 1. We're going to find three limits. First, the limit as x approaches -1 from the left-hand side, then the limit as x approaches -1 from the right-hand side, and then talk about the two-sided limit. So the only tools that we have so far to evaluate any kind of limit is making a table of numerical values and then looking at the graph. Ideally, we should aim to do both when possible. So let's start by setting up a number chart. We can put x in the first horizontal row, and then we'll put f of x in the row below. We are looking at two separate one-sided limits here, and then a two-sided limit, but they are all centered at -1, or they're all kind of looking at what happens at -1. So we'll put that in the middle, and let's just see what happens when we try to plug in -1. What is the value at -1? Well, up top we will have a 1. Down bottom we'll plug in -1, so we'll have -1 plus 1, and that gives us 1 divided by 0. Again, this is an undefined value. We can't have 0 in the denominator. This one is a little bit different than 0 over 0, which we've seen before. We have a number that's not 0 divided by 0. This actually tells us that we have a vertical asymptote at x equals -1. We can actually see that in the graph. We've got a graph that's got two pieces to it, shaped like this. Then at -1, we have another piece that's shaped like this. I can't show the whole graph, and your calculator can't either, but we do understand that this goes up, so we could put arrows on these in all directions here. We will talk a little bit more specifically about vertical asymptotes in a couple sections from now. So let's continue on and set up our chart. You should pause this video and see if you can figure out what x values that we'll substitute in as we approach -1. As always, I suggest choosing three numbers on either side. Here are the values that I would use, and then I hope that your values are pretty close. If you're having trouble when we're approaching a negative value with x, don't hesitate to draw a number line. Place the -1 here. That can help you decide, what kind of numbers we should be plugging in. You can even add another number like -2 here, and maybe 0 here. And remember that we're trying to get closer and closer to -1, which is the place we're finding the limit at. Again, pause this video and make sure that you are comfortable plugging in these x values into the function. Here are the values you should get when you substitute in these 6 x values. If we look at what's happening from either side, we can get an idea of what these limits are. So in part A, we want to find the limit as x approaches -1, but from the left-hand side. I know there's a lot of negatives here, but remember when the 1 comes after the number and it's kind of like up in the exponent position, that tells you the direction that we're coming from. So we're coming from, on the number line, something that's more negative. So from the left-hand side. Now look at the behavior of what's happening with our y values. We've got -10, -100, and -1000. These don't seem to be honing in on a particular value. In fact, they're just getting larger and larger and larger, but they're staying negative. You can test this by even plugging in a number that's in between -1.001 and -1, like -1.0000001. You should get a very, very large negative number. What that indicates is that the limit here is negative infinity. There is no particular numerical finite value that the limit is approaching on the y values. So we would say that this limit here is negative infinity from the left-hand side. This is what we mean by unbounded behavior. We can also see this in the graph because as we approach -1 from the left-hand side, the function just continues down, 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 and it will never actually cross its vertical asymptote at x equals -1. So for part A, we would say that this one-sided limit is negative infinity. For part B, we're looking at the other direction, as x approaches -1 from the right-hand side. Well, judging from our table, we see that as we get closer and closer to -1, our y values are getting larger and larger, but this time they're all positive. They're not approaching a certain finite value. They're just exploding and getting larger. You can even test this further by plugging in a number that lives in between -0.999 and -1, like -0.9999999, just kind of like mash on the 9 button, and you should get a very, very large positive value. So what that indicates to us by looking at the table is that the limit as x approaches -1 from the right-hand side of 1 over x plus 1 is positive infinity. Again, we can see that in the graph because as we approach -1 from the right, the function just keeps on going up and up and up. So the way that we notate that behavior is that we would say that this limit as x approaches -1 from the right of the function equals positive infinity. Again, this is an example of what we mean by unbounded behavior. There is no finite number that the function approaches. When this happens, we use the symbol infinity or negative infinity to describe that behavior. In part C, if we were looking to find the two-sided limit as x approaches -1 of the function 1 over x plus 1, well, these two aren't matching up. One is going down to negative infinity and the other side's going up to positive infinity. So when that's the case, we would just say that the two-sided limit does not exist. So we should be able to determine when we have unbounded behavior based on plugging in or substituting in a value that we're looking at the limit at. When you have a number that's not 0, like 1, and then a 0 in the bottom, that usually means that you have a vertical asymptote. What that should tell you is that the limit from one side of the value should be maybe negative infinity or positive infinity. And the limit from the other side should be either positive or negative infinity. And then if these two don't match, if you're looking at the limit at two sides, then that's a does not exist situation. We should also be able to decide which is which. Do you have negative infinity or positive infinity for your one-sided limits? We can do that by way of a table, and then we can check our work by looking at a graph. Again, we want to use both representations to double check our work and make sure that we're understanding what's happening with the function as a whole.